In this lesson, we want to talk about the performance analysis, in particular the bit error rate and simple error rate that different motivation schemes may experience depending on how the data travels from the transmitter and the receiver. And we start with bit error rate, and we say that it is defined as the ratio of total number of bits received in error to the total number of bits received in total for a large period over the large session of information transmission. And it is comes with an assumption that the total number of bits received is the same as that of the number of bits that have been transmitted from the source. It's always considered to be an average figure, and this parameter is very significant in determining the quality of digital information that is delivered to the receiving end, and it also indicates the quality of service provided by a given digital modulation scheme. So that is the intro to the bit error rate. And now we talk about the symbol error rate, in which case the definition says that the ratio of total number of symbols detected by the demodulator in error to the total number of symbols received by the receiver, that for a given period of time, that constitutes the symbol error rate. That is the ratio between the symbols received in error to the total number of symbols received. So again, it comes with an assumption that the total number of symbols received is the same as those that were transmitted by the modulator. Again, it's an average figure, so you cover it over a large period of time, and it is used to describe the performance of digital communication system. So to quantify, the next step is to quantify the bit error rate of a given modulation scheme, and we will start with the Ppsk, and we want to be able to find out how can we be able to quantify or express the bit error rate in terms of signal-to-noise ratio for a given modulation scheme. We start with the Constellation diagram of Ppsk, and we know that the symbol 1 and symbol 0, which is the same thing as the bit 0 and bit 1, are separated by pi, which is 180 degrees apart. And therefore, when they are represented in the Constellation diagram, the symbol 1 is represented with zero phase degrees, and the symbol 0 is translated with pi. So this is considered to be 0 degrees, is considered to be having pi radians, or 180 degrees out of phase. The difference between the energy of a given symbol is normally equated to be of value root ES or AB. So having said that, we say now that the signal that is transmitted over an AWGN noise channel, I don't know if we have defined the AWGN, but in few words we can say that a channel that characteristically is used to transmit the digital modulation scheme is over the air or wireless channel, and we say that when you transmit symbol X of T, then when you receive it on this side, it is going to be affected by noise that you can be considered to be additive, and therefore the received signal Y of T is going to be considered to be equivalent to X of T plus N of T. And what we know about the AWGN noise that this channel will introduce is considered to have the Gaussian distribution. And Gaussian means that the probability of receiving very small errors is higher than the probability of receiving very large errors. So that when you receive, this is the symbol that we are receiving. If, for instance, we are receiving a symbol S1, so if the symbol S1 has the magnitude of EB root, then, and we have said it has been affected by noise, then the probability that the received signal Y of T will be very different from the one that we expect. Is not very high. The idea is that it is going to be very close. So we are going to find very small values of NT that are added to our symbol energy of E root EB, and therefore most of them are going to be distributed near the maximum, near the value of XT, and not very many of them are going to be very large to cause a huge error or deviation from root EB. That is what Gaussian means. So for that reason, we say now that the signal that is received in error has this Gaussian distribution. the received symbols are going to be likely to be near the EB magnitude, and not very many of them are going to be far away. But then there is this small portion that crosses the decision boundary. Remember, we talked about the decision boundary at some point. That is the value over which, when a signal falls below it, then the signal is going to be considered to be opposite the one that was sent. So, for instance, if you had sent symbol 1, and some of the error causes this signal to be detected as symbol 0, then this portion of those errors are going to be said to be very significant, and these are the ones that are going to cause our signal to be received in error, and those are the ones that constitute the bit error. And that is why we say the probability of receiving those symbols, this symbol 1 as symbol 0, is our bit error rate. So we can define a conditional probability that says that the probability of receiving Y in error when X was sent as symbol S1 can be expressed as CDF function or as a cumulative distribution function when we know that the distribution of the noise is going to be Gaussian, and therefore this probability is the one that allows us to define the bit error rate. And therefore we say that the probability of error is sometimes equated to be equivalent to the probability the bit error rate, and therefore we can be able to calculate this probability of error as being equals to, we know that the whole of the area under this curve is equivalent to 1 or a unit. So, but then this portion is the one that is not in error. So the one that is in error is the one that is in blue. So we can say that if we say 1 minus this area under this curve, the bigger area, then you're going to find the probability of error. And therefore you can say that the probability of error is going to be equals to 1 minus the area under the curve, which can be found by integrating from 0. This is where we are saying 0 is to infinity, the Gaussian distribution function, or the PDF of the error, which is going to be 1 over root 2 pi sigma squared exponent of minus. Now we are talking about that Y is having mean of root ES squared divided by 2 sigma squared. We integrate that with respect to dy. So this is the expression that we define for us the bit error rate, or the probability of error. So at some point we can say that the bit error rate, again for the sake of clarity, can be equated to be probability of error, which is significant from the signal to noise ratio. But there is this very significant diagram that you find it in digital communication books that discuss the digital modulation schemes, whereby you compare the bit error rate with signal to noise ratio, or energy per bit to the noise spectral density. So this is the ratio which can be considered to be the same as signal to noise ratio per bit, and what we have been able to express is the bit error rate, or bit error probability, which is also considered to be PE. The one have been denoting as PE. Sometimes it's called PB, that is probability of bit error. So what we have been able to evaluate is that when we evaluate this equation, it is going to give us the probability of error, but it's going to be dependent on how much signal to noise ratio we are setting our signal receiver to accommodate. And therefore, before we talk about this graph, we should talk about the SNR, which is defined as the power of the signal received, power of the received signal divided by the noise power. From this graph that relates bit error rate with the signal to noise ratio, we see that this figure is equivalent to 10 power minus 1. This is 10 power minus 2, etc., going to minus 3, minus 4, power minus 5, 10 power minus 6. And what we are saying is that if we are setting 10 bits, one of them, or 1 out of 10, will be in error at this level. If we are setting 100 bits at this level, 1 will be in error. Similarly, for every 1,000 bits, 1 is in error. So as you go down, the bit error rate decreases. As you go up, the bit error rate increases. In equal measure, when we say that the signal to noise ratio is 5 dB. We know that how we evaluate the signal-to-noise ratio in terms of dB, we say that it is 10 log of signal power divided by the noise power. So if we find that this is equivalent to 5, that means this is always taken to be raised to 10. This means that 10 to the power 5 is equals to 10 divided by 10 divided by 10. This is 0.5. So 10 to the power 0.5 is equivalent to S over N. The log is not there. I'm just trying to simplify this so that what we are saying is that signal to noise is when we have 5 dB is equivalent to 10 to the power 0.5, which is equivalent to 3.6. And if we evaluate this equation here, that is the one that gives us the bit error rate curve or Ppsk, and that is the one we are finding right there. It's the one that is equivalent or almost appearing to be equals to the one for 4 p.m. For PM we are not going to be discussing, so this is the one for Ppsk. And what that means is that at 10 dB, the probability or the bit error rate is approximately equals to 1 error in every 800 or 900 bits. On the other hand, that is for Ppsk. On the other hand, for 16 Psk, the one that is in red here, at 10 dB signal to noise ratio, the number of the bit error rate that we are likely to experience is approximately 1 bit is in error in every 90 bits. So this was approximately 900. This one is approximately 90. So between these two, which one experiences high signal to noise ratio? And we can see that Ppsk has lower bit error rate of approximately 1 bit in error in every 900 bits in comparison to the Qps or B16Psk that has very high bit error rate of 1 bit in error in every 90. So what we definitely are sure about is that bit error rate of 1 out of 90 is way bigger than the bit error rate of 1 in 900. That is for sure. So what we are saying is that this one is for 16 Psk and this one is for Ppsk. And therefore what we conclude is that by the virtue that the bits in Ppsk have larger Euclidean distance between them, then the possibility of the signal that is received by the Ppsk, or this distance between the Ppsk is way bigger than the one for 16 Psk, and therefore the probability of error or the bit being in error is higher in 16 Psk than for the one that for the Ppsk or binary Psk. Now, if you look very keenly at this graph, you will see that I should actually label them. This one is for 32 Psk. The one in yellow is for 64 QAM. The one in stars is for 16 Psk. This one in blue and star combines the Ppsk. I suspect that Qpsk is here, and then what we also have here is Bpsk, and 16 QAM is also in this graph. So we have taken care of that, we have taken care of that, and that, and that. So P4 PM is also here. You can see an asterisk here. So this graph looks like it has combined multiple of them. 4 PM, and we have also taken care of and Bpsk. So this graph appears to be has 3 blues. All of them are passing through this curve, and therefore there is one question that we can ask ourselves, and that question is, if the 16 QAM has almost the same bit error rate or probability as 16 Psk, why then would we want to use such a lower motivation scheme which can carry only 4 bits per symbol, whereas 64QAM has higher bandwidth efficiency because it can carry I think 6 bits per symbol. So there is that huge question, and what we know is that when a signal goes through a channel that is not necessarily EWGN, but one that experiences amplitude variations such as fading, Ppsk is not affected as much, but QAM is hugely affected because what we know about QAM, it combines both amplitude and phase. So when the signal goes through a channel that has amplitude fluctuations such as fading, that point it may affect the delivery of QAM signals, and therefore that is the time when we would use the Ppsk, despite it having higher bandwidth requirement compared to QAM. So for that reason, we say that QAM is very efficient in terms of bandwidth utilization, and it experiences less bit error rate than the Ppsk, but Ppsk is very hard when you are sending signals that are passing through amplitude variation, because Ppsk itself is not affected by amplitude variation. So what we definitely have been able to establish is what this kind of graph means, that if you are transmitting at, say, for instance, 15 signal to noise ratio, that is what your receiver is able to accomplish, then what we have been able to establish is that a 16 Ppsk performs almost the same as 64QAM, despite the 64QAM having higher number of bits per symbol and therefore higher bandwidth utilization. So we are able to predict from this curve that such a 16 Ppsk would experience, say, approximately, if you see this is about 1,000, 2,000, 3,000, 4,000. If you say this is 4,000, that would mean 1 bit would be error in every 4,000 bits for 15 dB of the SNR, whereas for 32 Ppsk at the same SNR, you'd find the error rate very high. Approximately 1 bit would be in error per 90 or so bits transmitted, and therefore we say that depending on your SNR available or your bit error tolerance or probability of error tolerance, you can be able to use this graph to establish which modulation scheme fits your requirements best.